So I'm going to take just a single lesson and look at electromagnetism. It's another component of electricity that is used in your trade, especially your trade. It's actually used in most trades that have electrical components. And this is going to be more of a theory lesson. There will be a few calculations we'll do with transformers, just as example calculations. They're very easy calculations, but it's more a theory of how it works and why it works the way it does. There's not a whole lot of questions on this on your assessment, but I think it's a really good piece to include along with your basic DC circuit theory. So what we've been looking at so far is we've been looking at circuit theory. What happens when you have a DC current? So that's a direct current. So electricity just flows in one direction. It stays in the same direction. As we look at electromagnetism, we're going to start looking at AC current, which is the current that comes into our home. Now, oftentimes there's other electrical components that will convert that AC current into DC current for electronic purposes. But we're going to look a little bit at kind of the line in between the two. Hopefully you'll find it interesting and you'll maybe pick up a couple things along the way. So first of all, what is electromagnetism? So electromagnetism was observed when people found that putting current from a battery, could be current from an outlet, through a wire, if you put current through a wire and they're just tapping the switch here, they found by putting a compass over it, it made the compass deflect. So hence electromagnetism, electricity causing magnetism or interfering with magnetism is really what it happens to mean. So changing current results in a magnetism. It should be a magnetism, not an magnetism, but you'll have to forgive me there. Faraday was one of the scientists that worked with electromagnetism, and what he discovered was the law of induction. So what he found is that if you have a coil of wire, this is actually an experiment I'd love to do when I have people in class. I don't have enough resources to send home with people, but you take a coil of wire and you pass a magnet through it. And by passing a magnet through that wire, this time you're moving a magnet, we're not sending current, we're putting a magnet through a coil of wire, it actually generates current. Now that has to do with some of the nitty-gritty chemistry of how atoms are made up. They're actually magnetic, and that can cause electrons to move. Now, we're not going to deal with that. I had to do a couple courses with that stuff in university. Believe me, you don't want to do it. We'll just do the quick one lesson version. It's really interesting, but the math gets really heavy for it if you really want to get into it, and it can get really confusing really, really quickly. So changing magnetic field causes electric current. Changing current causes a magnetic field. So you've got these two laws that work together, and we often use them to help us out. So one place that we find electromagnetism is in solenoids, something that I know exists in the components that you work with. So the way a solenoid works is we have a coil of wire and we hook it up to a power source. In this case, we've hooked up to a battery. As the current goes through the coil, it creates a magnetic field inside. That magnetic field inside can draw a piece of steel in or anything that's magnetic. So it's often used for switches. So what there'll be is there'll be a metal rod that can be drawn into the magnet. And when it's drawn into the magnet, maybe it will create a contact. And wherever it creates a contact, that results in a closed switch, or it could result in an open switch. So we often use that for switches in order to be able to control them without physically touching them. In a car, and I know the car applications may be a little bit better because I haven't looked a lot at furnace electronics. I've looked a little bit, I've found a few of them in heat pumps, and it's always used to switch something on and off. Current hits a certain current. When the current gets to a certain value, that solenoid is drawn in far enough, a switch is triggered and an effect occurs. In vehicles, one of the places it's used is when you turn your starter switch, your starter on your car, so you turn your key over, there's a solenoid that engages and that sends current to your spark plugs. Your ignition coil, get my terms right, sends current to the ignition coil, which then creates spark, And ignition coils, they're actually a type of transformer as well. So that's actually kind of a cool feature. But that's how solenoid works. And I have cool little kits in my office that actually have solenoids in them, and you can actually kind of play and test and see how that magnetism occurs. Next year, we'll have to spend some time exploring with them. Unfortunately, you guys don't really get that benefit. Okay, so I'm pretty sure you've heard of solenoids before. Hopefully that's how they work, is they send current through, and we found out the current going through a wire creates a magnet. That magnet draws a metal bar inside, which results in a switch. Another version of a solenoid would be the way lights work. How you have those sensor lights that like leaving the college, we have these sensor lights, and your car pulls up and it senses that a vehicle's there, and then it switches. Well, usually it switches. Sometimes it's a little funky. But what that is that's the same kind of scenario. What they do is they have an electric current in the ground underneath of the pavement in the sensor area. When a car pulls into the middle, whenever there's a piece of metal in the middle of a solenoid or in the middle of a coil, it intensifies the magnetic field, which intensifies the current. And that's what those changes are, what the lights sensor triggers. So your car makes it feel more, you can tell that there's a magnet inside. Your car basically acts like a large magnet. You'd probably hardly notice, but it intensifies the current in the coil. And by intensifying the current in the coil, then it knows to trip the switch. So that's the definitely non-expert explanation on it, but that's the general principle. If any of you are an expert on it, you want to straighten me out, feel free. Just do it nicely. Electromagnetism is the whole principle behind how motors work, especially electric motors. So in this case, what you have is you have current. Now, current passing through a battery, and then it comes through and it goes through the coil. And as it goes through the coil, it creates a change in the magnetic field. Now, outside of that coil, there's another magnet. And you know how magnets, the poles want to line up? So this magnet, the south will want to rotate up to the north. The north is going to line up to the south. So that causes I guess a quarter turn in this case. Once they're lined up, there's what we call brushes. They're labeled here. These are brushes in the motor. And see how they have a split? So basically, once it rotates, that split allows the current to change again, which results in the poles of the magnet switching. And then, so now you have north and north lined up, and it wants to rotate down to south. And it causes this constant rotation. Now, that's for if you have an electric motor powered by a DC or a battery. Now, you guys know that a lot of motors, especially if you're dealing with heating, things typically aren't DC. It's usually AC current that you're using, alternating current. An alternating current, it alternates back and forth. And the constant alternation, the constant change in current means we don't have to rely on brushes to cause that rotation to occur. So that's one of the places where we use magnets. So they keep rotating as the current changes, the poles change, and it causes that rotation for the motor to continue to move. It's actually kind of cool. I always found that really fascinating, how motors work with just something as simple as a magnet and a coil of wire can make work so much easier, can do so many things. And I'll admit, every time I pull apart a tool or something, my husband laughs at me, because I'm always looking inside to find, especially if it's something that's mechanical, I'm always looking inside to find where's the coils. I'm always curious about where the coils are and what they do, whether they're changing voltage or whether they're doing something like, in this case, they're causing motion to occur. So it allows us to take electrical energy and convert it to mechanical energy. And this is just another step in the process. The current in the coil switch, the direction changes, and it causes it to keep rotating. So now, if you switch the current, it's going to rotate the other direction. That's all you're going to worry about. So if you switch the current, we just get change in direction and flow. Generators. I think there's lots of generators around here. Generators are basically motors reversed. So they work exactly the same way. In this case, the hand is acting as the operation. We'll often use a gas generator where we're using fuel in order to cause that motion. But as the hand turns, it causes this coil to turn inside of a large magnet. Now we saw that Faraday said if you could change the magnetic field inside of a coil or around a coil, it would result in electricity. And that's exactly what happens. As you rotate that shaft inside the magnet, electricity is generated and you can light a light bulb. You can, there's a couple cool experiments out there if you really want to play with it that use a drill in order to generate current. So you have a drill with a coil of wire around a magnet, and you can use it to light a light bulb. I haven't tried it. YouTube says it exists. And I remember, I haven't looked it up this year. I remember looking it up a year or two ago and going, I wonder if there's a way we can do that in class. And I just didn't have the supplies available at the time to do it because of some snow days. But you can take a drill and use that as your source of mechanical energy and actually use it to create current. I mean, kind of counterproductive, seeing as you have to charge the drill, but it's one of those kind of cool experiments to try build. I always like it when we can try build things in class. I'm sorry that you don't get that opportunity, at least not in my class. So transformers work on electromagnetism. So basically what a transformer is, you'll see there's two coils, so it's like two solenoids, and we bring them close together. Now, you saw at the beginning, I said, if you take a coil and you pass a current through it, it makes an electric field. And if we can bring another coil close enough, not touching it, but just really close enough, these arrows represent the magnetic field that's around. If we can bring it close enough that this is affected by the magnet that's created by putting current through the first coil, we can make current happen in the second coil. We call that the induced EMF, or the induced voltage, induced current. And they call that induction. So it's kind of a combination, and it uses Faraday's law of induction. It says if you put current through a coil, it creates a magnet. That magnet can create current in another coil. The power on a transformer will remain the same, or usually close to the same. As you know, transfers of energy are never perfect. So transferring energy from from coil 1 to coil 2 always does have a small amount of loss, but in theory, it would transfer exactly perfect. Okay, so we're going to kind of assume the theory of it transferring perfectly. So what this allows us to do is, if we can alternate the number of coils on each of the solenoids, we can change the voltage. Now, you know that electricity coming into a house is usually 120. And what we want to do for lots of times applications with heating, oftentimes you'll be stepping it down to 24 volts. And we'll look at how you would do that. So in this circuit, so this gives us the picture of a transformer. So you'll see that there's a little difference from the picture I had on the last slide. You have a coil of wire on the primary side. So you have a coil of wire on the left. This curvy line represents AC current. So transformers work best when you have alternating current, because you need change in current, which is why it's commonly used for household appliances. So you have alternating current passing through, coming in, and the current comes in and it goes through these coils. Now, we want to make sure that the magnetism that occurs gets transferred as much as possible to the other coil. So what they do is they wrap these coils around a piece of steel or a piece of metal. We'll say a piece of metal, could be anything. So the coil gets wrapped around a piece of metal. Now, the coils never touch. And in theory, because the wire's actually insulated, you don't actually have current transfer from the wire to the metal, the metal core itself, okay? So we're not looking at transferring electricity to this, but all we're doing is we put a piece of metal inside of it, and you know how metal is magnetic, right? So what happens by putting the metal in, it makes the magnet stronger. Because it makes the magnetic field stronger, it concentrates it, it means that there's more magnetic field over on this side. And by making more magnetic field On the right side, on the secondary side, we can generate more voltage over here. We can have a more complete transfer of the power. And as the coils are changed, the number of coils on the primary side and the number of coils on the secondary side will change whether the voltage is going to be increased or decreased. Okay, so that's how they work, and they're actually I find it really I find it fascinating how something that simple can be used to do something that, well, it can take electricity from being extremely dangerous and bring it down to being very safe with something just as simple as a coil of wire and a hunk of metal, literally. And you'll often find power stations. You'll see at the top of light poles, the round canisters, looks like kind of like a garbage can at the top of the pole. Those are often transformers. And what they do is they help step the voltage down before it comes into houses. Through power lines, you keep a really high voltage. The higher the voltage you have flowing through your power lines, you're going to have less of a power drop as current enters the house. It's to maximize energy transfer. So you transfer energy at high voltage and then you step it down as it comes into residential areas and into houses. So transformers are used all the time all around us. Now I do have a picture for you of a transformer that's used with a thermostat. I was looking at a schematic for heat pumps the other day, and I was looking up something on a schematic for installation for our Mitsubishi. We have Mitsubishi Mr. Slim. We've got a couple of them in our house. And I was looking up schematics because I was wondering about installation. Could I move it from one wall to another? Not that I would do it, but could it be done if I asked somebody to do it? And when it was interesting, because one of the first things I noticed was in the schematic, there was a wiring diagram, and I saw a wiring diagram that looks like this. Pardon my poor drawing. And that happens to represent transformer. The little bumps are your coils, and then you've got separation between them. So it was stepping down voltage between the line coming in, so from 120 down to an appropriate voltage for the, I think it was condenser it was traveling to. So in this case, we have a transformer here. You can see the picture. This represents our coils. And then you've got your two lines to show that they're separated. So this takes 120 AC voltage coming in and drops it to 28.5 volts to travel throughout the heating system. So furnaces, they typically operate on lower voltages, and that's how the high voltage in your house is converted to a much lower voltage is we use a transformer. We're going to see how the coil ratio will change what the voltage drop is. Now vehicles, your ignition coil in your car, what it does is it takes a 12-volt battery and it steps up the voltage to be about 4,000 volts, somewhere in around that range, in order to cause enough spark, in order to ignite the fuel, get your compression, combustion, and your whole engine cycle to occur. So for you folks, you're often stepping voltage down, but in vehicles, we take the transformer, we step voltage up. So there's a couple formulas really easy to calculate with. In the formulas, voltage of primary is directly proportional to the number of turns. So if I take the voltage coming in and I increase it, if I don't change the turns on the coil, it will increase the voltage on the secondary. N stands for the number of turns. So let's say I have 120 volts coming in and I want to decrease the voltage over here. What you do is the ratio of the voltage to turn ratio has to stay matching. So you would decrease the number of turns on the secondary if you want to step down the voltage. So more turns on the primary, less turns on the secondary is going to drop our voltage. If you have less turns on the primary and more turns on the secondary, it's going to increase the voltage and bump it up. Now, current and voltage work in opposite directions. So I don't know if you remember from first semester when we had direct and indirect relationships. This was the way direct relationships were set up. They were always two fractions, and if one component, the component on the top increased, the other component increases as well. But this setup where you have two pieces multiplied together were always indirect relationships. So what this one tells us is that if we take the number of turns on the primary, multiply it by the current, it will be the same as the number of turns on the secondary multiplied by the current on the secondary. So let's just think about what would happen. If I increase the number of turns, in order to keep this side matching, the current turns here are going to decrease. So more turns on the primary, less turns on the secondary. To keep this ratio the same, in order to balance it out, the current on the secondary is going to increase. So if you get a drop in voltage, that's great, but what it does is it bumps up the current. And you always have this kind of back and opposite relationship between voltage and current. And that's because the power from the primary always is equal to the power of the secondary, and power is voltage times current, or E times I. So if voltage goes up, current goes down, and they're inversely related. So you'll find because the number of turns is directly proportional to the voltage, if voltage goes up, the turns go up, then that means if voltage goes up, if turns go up, current goes down, because voltage and current are opposite. I'm not sure if that was really confusing or not. You'll have your equations. You can look them up. You don't have to worry about that too much. So we're going to do just I'm going to get rid of my video here and do a quick question with you. And we'll figure out, is this a step-up transformer, step down? I'll show you how to fill in a chart. And there's a couple questions, I think there's 2 questions out of all of the points available in your assessment that deal with the transformer, and they're nice, easy questions. So is this a step up or step down transformer? So step up, step down refers to the voltage. So will this transformer increase voltage or decrease voltage? Well, it has 30 coils on the primary side. So this is attached to our plug. So this is primary. What will we have on secondary? Okay, so this is the ratio we're thinking about. So if I increase the number of coils, then in order to make this, to keep the ratio the same, I also need to increase voltage. So this would be a step up. The number of coils is increasing, so it's stepping up the voltage. Okay, it's increasing the voltage, but we'll find as we calculate, it's going to result in a decrease in current. So in this particular case, let's fill our chart out. We have 120 volts on, 120 volts on the primary. We have 20 amps on the coil, leaving letters out or numbers out. And we have 30 coils. That's our N. And how much power do we have? Well, we can quickly calculate power. Power is going to be equal to current times voltage. So 120 times 20 gives us 240. 2,400 watts. And I've told you before that power on the primary and the secondary is the same, so that will leave us with 2,400 watts over here. And we know we have 600 coils on this side. How do we figure out the voltage? Let's start with voltage. So we'll use this ratio. 120 volts per 30 coils equals how many volts per 600 coils? So it's a direct relationship. Simply cross multiply and divide. It's 120 by 600 divided by 30. And we will find X equals 2,400 volts. To find the current, there's 2 ways you can do it. To find current, you could use this particular, that particular ratio, or you can just use your simple formula for power. It's not really going to matter which one you use. I'll use the turn ratio just because. And so the number of turns on the primary times the current on the primary has to be equal to
600 turns on the secondary times the current on the secondary. Okay, 30 times 20 is 600 equals 600I. So that must mean our current is equal to 1 amp. And if you look here, the coils, it's 20 times the coils, 20 times the voltage, and you'll find 1/20th of the current, right? So pretty easy calculation, nothing too complex. Hopefully that works out okay for you. Let me know if you have questions, or let me know if you found that interesting. I'd like to know what your thoughts are when you have a chance. We'll do one more calculation, and then there's a worksheet that you can work through. Just as a few practice questions, and there's a couple practice questions in a SAM quiz as well. So we have an input voltage this time of 220, 30 amps of current. The secondary has 5,000 coils and 15 amps. I want, oops, not 15, 1.5 amps. I want to know how many coils are on the primary. So we're going to use this formula. So the number of turns on the primary times the current on the primary, which is 30, has to be equal to the number of turns on the secondary, which is 5,000 times 1.5 amps. By the way, would this be step up or step down? Your current has decreased, so that must mean our voltage has increased. We'll find out when we calculate. Divide volts by 30. The number of turns on the primary, 5,000 times 1.5 divided by 30 gives us 250. The coils are increasing, so this is definitely a step up. If I want to know what the voltage happens to be, we can just use our same ratio. 250 for 220 volts is equal to X volts over 5,000. And that gives us 4,400 volts. And then to calculate power, again, you're just multiplying voltage and current. So 2,000 or 220 times 30 gives us 6,600. And that means over here, we're going to have 6,600. And that would be watts. So easy calculation, not really too much to them, pretty simple. And that finishes off this section. So that finishes everything off for electrical. So I have the quiz posted for this section. There's also an assessment for this section. I'll put a quick video up just going over what I want you to do with it. And that has us finished electrical before break. Your assignments won't be due until the Monday after break, but feel free if you want to finish them up this week, and then you won't have to worry about anything over the break.